Hello, my name is Manuel Freire, and I'm going to present accelerating the analysis stage of sparse triangular solver operation. In the past 15 years, the HPC landscape changed a lot. The main change, or one of the main changes, is the introduction of GPUs for general purpose computation. the GPUs have a lot of cores, so they have a lot of parallel computation power, and if you can parallelize, divide your problem and parallelize it, the GPUs outperform almost every other hardware. So for HPC, they are the go-to, and that makes that there are a lot of good and efficient implementation of blast routines. The sparse triangular solver is the operation that solves a triangular system that the coefficient matrix is sparse. It has a lot of important applications, such as iterative solvers for linear systems and the computation of eigenvalues and eigenvectors. The triangular solvers in general, also the dense one, have present a challenge in the sense that they are iterative in nature because the unknowns or the rows depend from the ones that are before. So you can't parallelize in the way that sparse matrix vector multiplication can be. So the sparse one has also another problem, that is that not every row depends of all other rows before it. So there is a variability in which you can process the work. So rows can be processed in parallel if none depends of the other. The applications of sparse triangular solver makes that in many times you have to solve different systems, but they share the coefficient matrix. So there is a lot of work that can be reused. The sync-free paradigm is motivated because of the increase on computation power. So the idle time is penalized. The the main problem is the synchronization with CPU. So algorithms that avoid this synchronization can make huge gains in computation time only because they have better occupancy. In this work, we revisit the sync-free level set routine proposed by Dufrescu et al. We analyze the main bottlenecks of the first step, that is the one that does the common work in the systems that share a matrix, and we divide it in a series of self-contained stages and propose changes to parallelize one of them. There are two widespread paradigms that we want to mention. One is the level set strategy. The one is used by QSPARS and interprets dependencies as a directed acyclic graph. The idea is that they find a level structure. For example, like with BFS, and the nodes for the same level can be processed in parallel because they don't depend one from the other. The other paradigm is the self-scheduling. The idea is not to use a pre-calculated order, in the sense, for example, in NVIDIA GPUs, if the order depends of the thread ID, the designation of the thread ID, and the block ID is a static one. But the idea is to make a pool of tasks, and when process or threads are ready, they take one from each. There are two previous work that are important for our work. One is from Liu et al. That proposes an implementation that avoids the cost of synchronizations in GPUs, and the one we already mentioned, the Freire et al. They proposed a two-step GPU implementation. The first step is the one that does the analysis, and the second one is the one that does the solving. The analysis have a few objectives. One is to sort the rows in a way that the rows that are first in the don't depend from the rows after, and other is to calculate the size of each row. That's a bit tricky because we don't calculate the size, but the size class, that is rows, for example, 3 elements and 4 elements are one size class, and we don't take into account the element in the diagonal. Other objective is to group smaller rows to be processed by the same word. That's why we use a idea of size classes, so we can group rows that are similar in a sense. We divided the analysis into 8 stages. T1 does the initializations. T2 calculates the level structure. That is a kernel, is in GPU. T3 transfer the structure to CPU because the matrix was in GPU at start and will be when we finish. T4 and 5 order the rows and calculate the size. That's one of the main objectives. T6 that's the other main objective, that is grouping rows that will be processed together as one task. And T8 and 7 transfer to GPU again and free the memory, the auxiliary memory. We found that 3 tasks, 6, 7, and 2, were more than 80% of the computation time, and from them just T2 was in parallel. The implementation of T6 iterates for every row after they are ordered and decide if grouping it with the row before. So, since we know that the rows that have a different level or a different size class won't be grouped together, we can do that work independently, even if it is iterative. There are iterations that can be done in parallel. OpenMP is a public library to manage threads in CPUs. It has primitives to parallelize loops, for example, parallel for, and allows to configure the maximum number of threads that it will create and a strategy to assign these threads. Our idea is T6 has iterates 2 times. One is a symbolic iteration in the sense that just want to count and known memory requirement to malloc memory, and after that does the grouping. So we divide every one of these two loops into two nested loops. The one in the out is the one that iterates for the pairs size class level, and the one inside is the one that iterates for the rows of this pair. Since we have parallel for, we can parallelize the outer loop and improve the execution time. The hardware platform, Intel Core i7 and an NVIDIA 2080. The data type is AEEE single precision, and the test cases are 22 square matrix of the Swiss Farm matrix collection. The matrix collection is the formerly University of Florida. As you can see, there are a lot of different dimensions and non-zeros, and also we track the level structure, the number of levels that has, and they're different. In our evaluation, we just focus in T6 and tried versions with different number of threads, 2, 4, and 8. This is the execution time of the four versions: the baseline that is in CPU and the in serial, and the others that are with OpenMP. As you can see, OpenMP wins in 14 versus in the version with four threads wins in 14 matrices, and the versions with 2 and 8 are behind with 5 each, and the baseline wins in 2. This is not some wins are shared. That's why these terms add up to 22. In the matrices that T6, the better T6 is the baseline. This stage has almost no impact because it's around 1%. The version with 8 threads is the opposite. When it wins, are in bigger matrices, and the T6 is important, but the difference with the others in absolute time is not much. And the version with 2 threads has better results in some matrices, but in them have a similar results to the version with 4. Our final remarks is we revisited the implementation proposed by Dufresne et al. And focused especially in the analysis routine. We performed experimentation to evaluate the bottlenecks, and we found 3 stages that consume 80% of the time. We developed a new parallel version for one of the main bottlenecks. That the idea is that relies in some independence in its iterative nature, and we divided the main loops into 2 each, so we can use OpenMP to try a different number of threads. Even if no number of threads that perform the others, it's a good guessing rule to choose always the version with 4 threads. In our future work, we want to test our implementation in more matrices. One idea is to test in all square matrices of the collection. We want to develop an adaptive strategy to choose for the 4 variants. It's tricky because the gains are not so big, so the strategy has to be really fast to don't lose the gains for choosing the best variant. And we want to attack the other 2 bottlenecks. The idea 45 is try an approach, a parallel approach, and 42 we have to do other optimization because it's already in parallel. Well, thank you very much. That's all.